Cool, thanks for coming. Just a bit of housekeeping. So the toilets, if you've already found them, are at the back to the right. I think you've got to press the button, so you could get locked out, so make sure you press the button before you leave. Also, we are looking for different venues. So if any of you work at a company that is interested in hosting one of these meetups, come see me, because we can organise future meetups at your venue, and we'll give you a talk. Cool, so yeah, thanks everyone for coming. So Addy's going to kick off with all things streaming. We're going to hold the questions until the end. We're going to rattle through the talks, and then the questions will be at the end, okay? So yeah, cheers Addy.
Thank you. Super excited to be here, and I'm super excited to see familiar faces. Hello everybody. Today we're going to talk about data streaming. It's kind of like the right meetup to be at to learn about data streaming. I'm going to go over some patterns. Some of them might look familiar to you. Some of you already implemented it, but maybe some of them will, create some curiosity and inspire you to think slightly differently. So let's jump right into it. What is data streaming and why is it so hard? The reality is it's data, it's everywhere, it's the backbone for analytics, it's the backbone for machine learning, it's the backbone for BI. Anything that we do requires working with data. And data streaming is kind of like a couple of people that came together with some experience in other data fields and decided, hey, we need to make it faster, we need to make it more reliable, we need to build it in a way that latency is what we want, throughput is what we want, and so on. And usually the two types of people that comes into data streaming, first of all, experienced folks. Folks with 2, 3, 4, 5 years engineering experience in the industry, either coming from a batch world, from an analytical world, from a backend world, building, knowing well about schemas, building all the different jobs and pipelines and so on, or perhaps DBAs really know how the internals of a database works and so on, how to optimize these things. And the other side is applications. We need to do something really, really fast. MySQL, Postgres, whatever your favorite database works enough, good enough. We don't need anything else. And so we're building applications kind of end-to-end, back-end, UI, perhaps, and so on. And this is where kind of data streaming merge. We need both skills. And this is what makes it a little bit harder to actually implement in organization. And hopefully these best practices are going to help you make decisions around the architecture today. So a little bit about me. I wrote 2 books for O'Reilly. One is on scaling machine learning system. The second one is High Performance Spark, the second edition. I'm a people manager. My background is software engineering. I did software engineering for 10 years before moving into management. And I work in streaming. My background is in big data field and machine learning. And then after that, I moved to streaming. And I work for Confluent, the company I believe everyone knows, right? Everyone heard about. Okay, cool. What are the challenges? There's a long list of challenges. We're not going to solve it all, but there's going to be a couple of them that we will cover. We're going to talk about exactly one semantics end-to-end, not the classical just with Kafka or just with Flink, but how we connect the systems together to get the semantics across the different tools. Join operations, why they're so annoying and what we can do about that. Complex event processing, we'll think about time, we'll think about some aspects of related to them. And guarding the gates. What does it mean? How do we build a system end-to-end where we're enabling new engineers that are coming into this space to build the right tools and the right pipelines that we need them to build? So let's jump into exactly one semantics. In order to understand that, we need to understand some of the basics of data streaming. Data streaming fundamentals usually talks about 3 different criteria that we have to know. One is events. We live in a world where every click, every transaction, every activity that happens generate an event in our system. Second thing, we have to think about state. What does that relate to if we're building an application or we're building a data streaming pipeline? Do we care about state? Can it be, must it be state? Can it be stateless? This is going to impact what we're building and the complexity of our system. And lastly, we need to think about the aspect of time. What does time mean in our system? How do we decide what exactly timestamp represents? And this is where things start to get a little bit complicated, because time means different things for different components in our system. When we work across teams, when we work different engineers will define timestamps as slightly differently. So you start seeing things like timestamp 1, timestamp 2, you don't know, you need to merge a couple of tables now. There's a couple of streams coming from different places. How do you make that decision? Who is right? Well, everyone are right. The question is, what do we need? Relatively, there are 4 different types of time in our system. One is when event just was generated by some edge machine or by some application. The second one is when we wrote that event to storage. For example, if Kafka wrote it now to the brokers, this is a timestamp that we have. Third one is ingestion. When was this event ingested in the system? We can think about Flink ingesting events from Kafka, for example, starting to processing it. Ingestion by itself could be a timestamp, and processing by itself could be another timestamp that we can relate to. Now, what are the challenges when thinking about these different time aspects? The challenge is that we have 2 of them that are deterministic and 2 of them that aren't deterministic. What does that mean? That means that, for example, if I have an event time of when the event was created, this is immutable. It's not going to change ever. I can trust it. Once it's created, it got a timestamp, that's it. It's true for event time and it's true for storage time. The second aspect of the world is mutable. It means non-deterministic. So, for example, the 2 timestamps that are non-deterministic are inject and pre-processing or processing. And the reason for that is because I can reprocess things and then I'm getting a new timestamp. So once I'm getting a new timestamp, I have to think, do I really want that new timestamp of when the data was processed? Or do I want the timestamp of when it was created? What is the value for me? The advice, best practices, as always, think about the immutable aspect. Easier to debug, easier to work across teams, easier to explain the use case and what it is that you're building. So this is one practice around time and calculations. So again, we want the event time, we want the storage time, less about ingest and processing. And now that we have time, we can start thinking about what it means when event is late to the system. This is usually when we get a little bit, things get a little bit more complicated because we have to, this is also why we want a timestamp that is immutable, because we can say the event was late for a specific reason and it's not going to change, it was just late. Versus if we have a mutable one that is getting more complicated. So if I have a timeline, right? Timeline goes here from left to right. I have a specific watermark. The watermark tells me what are the events that were processed until now. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3 until 5 got processed. Every timestamp that comes after 5 is going to be on time. Every timestamp that arrived after 5 that is smaller than that specific 5, my watermark, is going to be considered a late event. And for late events, I have to make decisions how I'm going to process them and if I'm going to process them. These are another patterns that I need to decide on. What do I want to do? Usually, sometimes we'll create a small window for late events that we're waiting for. Sometimes we'll put it in a separate queue for the future if we need to debug something in the system, and so on. But again, we always want to have them. We don't want to throw the data. Throwing the data away, it's a practice that I've seen with many engineering teams. But usually when we want to debug, when problems occur, this is where we want to be able to look at what didn't work out. So these type of events. And if I'm throwing that away, I don't have a clue of what happened in my system. So another thing to think about when events are late. This is another example of where events are late. You can see in the top, the stream is in order. You can see the watermark 11 right up there. And everything on the right side of 11 is going to be on time, and as well as on the left. On the bottom side, you can see that on the right side of 11, you see the number 12. We shouldn't be there, right? And the number 15. So we talked about time, we talked about mutability and mutability, we talked about the challenges of deciding those. Now that we have time, we can look into windows. Anyone here worked with windows of data streaming? See some people nodding, raising their hands. It's okay. It's a data streaming event. What are windows? Windows are time-driven, which means we need to know the timestamp. We need to know the boundaries of where we're living at. Windows enable me to allow late arriving data. So anytime there's a late event, I can capture it within my window, and it's going to work. And there are different types of windows that exist. Specifically, I'm going to talk about Apache Flink. The first one is tumbling window. It's kind of like what you think is the classic window. We have the size of the windows, and every time we're reading the same size. There's no overlapping in here for a specific reason because we don't need it. So things like aggregation, running sum, running average, and so on is going to be a classic use case of a tumbling window. Another use case is sliding window. Sliding window is when things get a little bit more complicated because it doesn't, I can have a specific size of window, but again, my sliding window can decide how to jump forward in time. So I can definitely get this overlapping of windows. This is great for use cases, for example, where you have an antenna somewhere and you want to calculate how many phones are in the area that you need to give service to. So for example, every second here matters because you want to know how many services you're providing. And so you want to know it for the exact time. You don't care about moving the whole size of the window forward, but you want to have this kind of like sliced by events. So just something to think about. Usually at big events, big concerts, there's always a problem of services. I don't know if you ever had a problem of service in a big concert, but yes, this is one solution that is being used. Last one is session windows. Session windows is actually an optimization window. Anyone here heard about session window? A little bit. Okay, cool. Essentially what it means that my system knows when to get into idle. And that's a good thing, because when my system goes into idle, my cluster can essentially shrink if I need to. So I can scale up and I can scale down my different resources according to the events that are coming into my system. If I don't have a continuously stream of events coming in at relatively a rate that I can predict, this is a great use case where I want to have an application that is always up, data streaming application that is always up but doesn't consume all the resources in my cluster, so I can scale up and scale down when necessary. Here I will need to define what is the size of the window that I'm willing to wait. For example, I have my cluster with, let's say, 100 machines, and then for 5 minutes I don't get any events, I can scale down, and then once the next event comes in, I can scale up and start running with the system. So how do we going to put it end to end? So we talked about time, we talked about windows, but in reality, we wanted to talk about another aspect of putting the data streaming system end to end. And we know Kafka gave us the capabilities of moving data super fast, and Apache Flink gave us the capabilities of processing data streaming with the fundamentals of Flink, like I talked about before, the fundamentals of data streaming. And so we are able to connect all this system to work together. With Kafka giving us the timestamp, Flink knows how to create the windows necessary for it, and so on. So the next question that I want to ask is, how do we build it end-to-end with exactly one semantics? Anyone here heard about exactly one semantics? Hopefully everybody. If not, I can explain. Okay. Exactly one semantics, like most of you know, I didn't see everyone hands up, so I'll just explain it very quickly. Means I'm processing the event exactly once. That's it. Not at most once, not at least once, but exactly once, which means every event in my system has to be processed exactly once. Think about, bank transactions, classical example. If I process it more than once, I'll get duplicate of transaction. There's going to be a problem down the road. If I won't process it at least once and I get zero, at most once and I get zero, then again, event that got lost, transaction that got lost, someone is going to get mad. So how do we build that when we look at Flink and Kafka working together? Flink released an algorithm some years ago on building exactly once end-to-end. And the way they build it, they expose an interface of something that we need to implement. This is the two-phase commit interface, something that was recently released in Kafka. Many engineers up until a couple of months ago had to go and implement them themselves, and finally we have it in Kafka as part of the open source, so it knows how to integrate together with the exactly once of Flink. So here where you're actually seeing different parts of the Flink architecture, where we have kind of like Kafka to inject data into our system, and the rest of them are Flink. So job manager, data source, Windows, data sync, state backend that Flink knows how to manage are all Flink components. So when data is being injected into from Kafka, the Flink job managers know how to inject what we call a checkpoint barrier. Checkpoint is our mechanism from distributed system to knows what happened in the system right now. It's kind of like a checkpoint. We're saving information to disk. The next thing that happens, the data source kicks in, and the data source is going to speak with the state management to send a snapshot offset of what's currently happening in the system, and it's going to pass the checkpoint barrier to the next task, to the windows. The window is going to process the window as we expected, and it's going to do another checkpoint. Remember, each one of those components are going to talk with the state management to make sure they have the snapshot state where we need it to be. And then the windows, again, pass the checkpoint barrier to the data sync. The data sync snapshot the state, and then at the end, pre-commit external transaction go into Kafka. Again, external system outside of our Flink. And lastly, the job manager talks with all the different components to make sure everyone gave us a green light and agreed. If any one of that fails, it's going to revert the whole process up to the last checkpoint where it has some agreement around, and then it's going to run it again. And this is how exactly one two-phase commit works in between different distributed systems, specifically with Flink and Kafka. And lastly, of course, committing the external transaction to Kafka, making sure end-to-end give us exactly once. So let's pull it all together. Each one of the operators creating a pre-commit. At least if one fails, reverting, starting again. After a successful pre-commit of all the systems, of all the parts of the system, the whole system at the end gets an approval. This is exactly one semantics end-to-end. Let's talk about join operations. Join operations group usually split into two. One of the hardest things about data streaming, since most of you build applications, is actually thinking about the joins. What keys am I going to join on? Is that going to be a join from historical data? Am I going to bring some historic data into it, what we call join between stream and batch? Or is that going to be join between two streams that now flow into the system, and I need to define a join that makes sense around that? So if I have join between stream and batch, it's usually an easier way to go about it. You can think about kind of like if you're coming from a database world or a data space, you can think about it as a lookup table. I have some lookup table, I have some data that's got streamed into the system, and I'm going to do join by the different events that I have in there. And so each event that came in, for example, views and clicks, is going to be matched into a stream of join results right away. This is a straightforward pattern. There's no magic behind it. When I have streams, this is when challenges usually occur, because here I have to think, what am I joining on, right? I have windows, right? There's a notion of windows, and there's a notion of keys that I want to actually run the join. And so it could be that some of the elements won't show up in my last join result. Some of them got late, some of them never occurred, right? You can see, for example, B started, we have it in views at 1, B at clicks at 11. What do we do about that? Now, there's an interesting pattern that I decided to call it puppy shelter. I thought it makes sense when working with the teams. Essentially, we call it the lost events. Events that got lost in the system, we want to put it somewhere in an external queue, kind of like a puppy shelter, and decide how we want to go about that. Either we want to send them back into the stream, somehow thinking about that, or we want to match it later on, or we want to run some queries or analyze this situation. But we do want to make sure we're not just dumping it somewhere. We want to take care of that, and we want to make sure it exists. There's not always going to be the best solution. It's really case-by-case scenario, because here we need to look into the tables, the data, the use cases, what got into the system. It's never going to be perfect. Don't try to make it perfect. It's not going to work. But the public shelter will help you keep those friends in a group where you can actually investigate it. So think about that as a pattern when you are building when you're building stream join. And lastly, let's talk about guarding the gates. Data integrity, for people who comes from the database world or the analytics space, knows it's probably one of the hardest problems in the data world, because all the data comes from upstream. And once the data comes from upstream, we kind of lose the source of truth, which makes it very hard to make decisions what to do with the data. Many data engineers just dump the data somewhere and lose it. But here I'm going to suggest a different solution for that, which is going to challenge a little bit some of our thinking around data streaming. And for that, probably you'll have lots of questions. So data integrity talks about the physical integrity of the data, talks about the logical, and talks about the referential. Three things that are very important that feels like big words, but at the end of the day, it's data cleansing and data validation. That's it. We want to make sure it's the right format. We want to make sure we got the data in the right place. And we want to make sure we don't need to clean or put any default value where we need them to be. And it's true that in distributed systems, and not only, bad things happen to good data. When our system goes through serialization, deserialization, multiple steps, moving from place to place, maybe type promotions if we're working with different formats, Avro to Parquet and so on, it could be that suddenly we'll get null values. And null values are not great when we're running things like SQL. It's going to give us an error, this specific thing, and it's not going to work. So what can we do about it? And here it's slightly when we're getting opinionated around Kafka, because Kafka is kind of like Switzerland. It's kind of like neutral. It's like, I don't care about schema. I don't care about what you put in there. Put whatever. It's chill. It's whatever you want it. You can just put it. But in order for us to actually serve something related to analytics and machine learning down the road, these folks start to care about schema. And so what do we do? Do we keep it kind of like more chill, high level, not trying to attach any schema to it? Or do we want to start thinking about schema upstream closer to the source of truth? Now, there's a lot of opinions and there's a lot of use cases. There are specific use cases where we do want to think about schema upstream. This is when we have what we call the defined data product down the road, and usually not when we just want to move data from system to system without validating it. But again, here in specific, we want to talk about guarding the guards and helping the system actually build what we want. And especially when we want to bring new engineers to work with us, we want to make sure to help them putting the right guardrails in place so they're able to, we can enforce it in the system much easier through programmatic ways. I'll show you in a second, instead of, sending 10 Slack messages hoping that things will go well or commenting on, on a PR. So Kafka has producers and consumers, and we have the brokers in the middle. And some of the things that usually stink in data integrity, these are schema validation, usually really annoying downstream, schema evolution, schema changes. Maybe all my producer haven't yet decided about the update for the schema, but the schema did change in the system. So what do? Do we wait for everyone to finally upgrade it so we can do something downstream, or there's better ways for us to actually enforce that? Input validations, type, format, range, all these things that, if I'll just get null values at the end, I'll have to dump the whole row somewhere, and it's not going to be pretty. And other smells. So this is where things like schema registry can actually help us. The schema registry is kind of a repository somewhere that helps us manage the schema and manage the values that exist in the schema. It also takes care of versioning, validation, and interoperability, and I'll show you in a second. Many people that looks at schema registry think, oh, it's just enforcing the schema, and it's true. It is a contract enforcing the schema, but it's even smarter. We can create rules to validate the data as the data flows, and decide that if the rules aren't applied, we can send it to a dead letter queue, kind of like another Kafka topic somewhere where I can analyze that, and it's going to continuously flow in the system without the intervention of an engineer doing that, because the data is going to flow automatically into my dead letter queue, and I'll show you in a second. So if I have a producer service sending some serializing data with schema that it got from my schema registry, Kafka broker is also going to enforce it, and then the serialization happening on the consumer side, it's also going to enforce that schema rule. But how do we define validate? I want in between those, I don't want my engineers to write any code validating the schema at all. It shouldn't be hard-coded into the code. I want to make sure it's outside somewhere in a JSON file where someone who is responsible for the data product, who knows how the business should operate, is able to go in and update it. This is where I have my JSON here. So this is a snapshot of a JSON where I can define the schema. And within that, I can write common expression language. This is of kind conditional, where you see if the message .name means I have a field with name is not null, it's good. But if it's null, on failure, send it to a DLQ, a dead letter queue, another Kafka topic that it's not my original Kafka topic that I wanted to send it to, but somewhere else where I can investigate so it won't harm my stream down the road. Again, critical, enable me to enforce it. Every engineer is going to try and send bad data. His events or her events are going to be sent to a deal queue. We can create alerts on this deal queue. We get a better guarded system. Second one is schema evolution. So this is, we didn't call it exactly schema evolution. We call it transform a field. One of the things with schema evolutions, for people who come into the database world, you know that we can always add columns. We don't really delete any columns. So if my schema evolved to a new version, I'm adding a column. The column would usually get a default value until all my systems that producing those events are going to be adjusted with the new value that they need to produce. And here, my schema registry can help me enforce default values upstream. What does it mean? It means it can transform a specific value in my event, in my row. Here you can see some expression. Maybe some of you would recognize that it's kind of like a Java expression. Name, full name, and value. If value is null, take the first name, put in the last name. Otherwise, take the actual value. So this is how we can create another field, another value when my schema gets through a schema evolution. There are many other things that we can do with transform, but usually the best practice is to keep it to schema evolution so things doesn't get messed up. But this is a great way to enforce adding a new value there. So let's put it all together. We have Kafka ingesting data. We have schema registry, help me to enforce everything I need to enforce in the system. We have Fling that helps me process things in real time, and then syncing data back into Kafka and sending it to the end user, either dumping it into an iceberg or consuming it from an application. So we talked about all these topics, and I'll do a quick recap. I believe we're at time. Data quality matters. Deal queue, dead letter queue is a friend. Use it. If you haven't used it before, this is the time to add it to your system, to think about it. Schema registry helps you enforce it really fast. You don't have to hard code anything into it once you have schema registry. Exactly once end-to-end is finally here, in the open source specifically. You're most welcome to use it and enforce it. This is probably one of the hardest things in distributed system because it goes beyond your own framework, and you have to work with another external framework to do that. Join is hard. Use the shelter puppy. At least it will give you a path forward to investigate. And you need to think about string planning when you work with join operations. It's always hard. I don't see a world where it becomes super easy with data streaming or even classic analytics. But plan for it. Thank you so much. I just want to, I appreciate it. My friends at Confluent gave me a skip the paywall code, which means you can use $400 in Confluent Cloud without the need to put your credit card into it. If it's something that you want to play with, if it's something that you're interested to learn what exists out there. So no credit card. It's nice. yeah, happy to connect with you on LinkedIn. I think LinkedIn is the place. And yeah, that's it. Thank you so much.